So you've got a blank page. You got a blank page on 667, but there's enough examples that you might want to start on page 666 in the white space there, and then you can move into page 667. So we're going to look at how identities can be used in solving trig equations. And we've done a bunch of this already. In fact, we even started this in chapter 6. So in chapter 6, we had those questions which had two trig functions, a sine squared and a cos, or a cos squared and a sine. And then you had to use the big idea that sine squared plus cos squared equals 1 to substitute in, so you only had one trig function. But now we're going to look at ways we can do that as well with double angle formulas. So here's our first example. Solve for theta, and we have a cotangent theta equal to 2 cos theta. So one of the things you would look for is if there was a way that you could change everything to the same trig function. Like if it was cotangent and tangent, then you could change everything to tangent. But cotangent and cos, we can't change everything to the same thing. So this is where this last strategy is going to come into play, right? Just like in proofs, sort of a last resort, or like a common thing, you could change things to sine and cos. So I can change cotangent to cos over sine. And then I could multiply both sides. It is an equation, so you're allowed to multiply both sides by sine theta. And that, of course, would get rid of the fraction. Oops, and I did not write it correctly here. There we go. Multiply both sides by sine theta, and then you would have 2 cos theta sine theta on the right-hand side. And this is where you are going to get tempted to do a mistake, okay? If you want to divide factor instead. Because right now, the very first strategy that we listed, which was get it to just one trig function, which is an important strategy, can you see that if you divided both sides by cos theta, the cos thetas would go away and you'd only have sine theta? And you'll be very tempted by that. But I want you to look at this equation right now and notice that if cos is equal to 0, both sides would equal 0. That would be a solution. If cos is 0, the left side would be 0, the right side would be 0. And that would be a solution. And if you divide by cos, you might be dividing by 0 or getting rid of a solution that you need to consider. So how do we factor instead? Well, for factoring, we like to make one side equal to 0. So we're going to move everything over. And what you wanted to divide by is a common factor. So we can factor out that cos theta instead of dividing by it. And then with our factored form, this allows us to say cos theta could be 0. And here's the other one you would have got had you divided, that sine theta is equal to a half. When is cos equal to 0? 0, pi and 2 pi. When is sine equal to a half? Quadrant 1, quadrant 2, pi over 6 family. Okay, again, we get used to solving between 0 and 2 pi. This is where I have to go back and reread my question. Yes, my domain was between 0 and 2 pi, and both 0 and 2 pi were included, so this is good. Sorry. Good. Okay. Part 2 of using identities to solve. When you have a 2 theta inside of cos or sine, up till now, those have always been part of multi-revolution questions. But now that you've learned double angle identities, sometimes it's better to use a double angle identity, sometimes it's better to use a multi-revolution strategy. This is one of those examples where you learn something new and it makes something that you knew before, which you're like, oh, I'm pretty good at that already, it makes it harder because you learned something new. That happens lots. In mathematics, that happens all the time. Things are straightforward, they're good. You're like, I can always do trigonometry, a squared plus b squared equals c squared. And then like, oh, but what about not a right triangle? And then you start doing a squared plus b squared equals c squared when you shouldn't. And then you sometimes use like sine law when you could have just used SOHCAHTOA. Because you learned something new, it makes something previously more difficult. So what we have to do is we have to look at where are the times that one strategy would be best and where are the times that another strategy would be best. So for our multi-revolution questions that we've done already, if it only has the trig function with the double angle, and just numbers and other things besides that, then multi-revolution would be the best strategy. But if you have the double angle and another trig function, then you'll want to use a double angle identity. Good. Can I slide down? Like to there. So let's start on the one that we've done already. Not quite? Okay. I'll wait. So our multi-revolution question, you've done these before. Let's get the 2x, cos 2x equals root 3 over 2. Review of multi-revolution questions. First, you write your domain now for 2x. So x was between 0 and 2 pi. 2x would be between 0 and 4 pi. Then we solve for 2x between 0 and 4 pi. When is cos root 3 over 2? That's your pi over 6 family. Quadrants 1 and quadrants 4. That's the first time around. The second time around, how good are you at getting coterminal angles? We'd have to add 2 pi, which is 12 pi over 6. So you're really only having to add 12 to the numerator there and 12 to the numerator there. Then to solve for x, divide by 2 or multiply by a half. So this is something we've done already. But if you have a double angle and, as you see in this equation, there's another sine x, then you're going to need to use one of your formulas. If it's a cos 2x one, you have to choose the formula that makes everything the same trig function. In this one, we only have one choice for changing sine 2x. We have to change it to 2 sine x cos x. Only the one trig function with that double angle, yes. Method on the right, as soon as you have 2 trig functions, now here you're going to be tempted to divide. So instead of dividing, move everything over to one side and factor out the common factor instead. So where is sine equal to 0? At pi over 2 and 3 pi over 2, where is cos equal to a half? That's your pi over 3 family, quadrant 1, and quadrant 4. Again, double check your domain. It was between 0 and 2 pi. So we're good. 3 pi over 2. But now we're ready for example 4. The hardest of the ones that we've had so far. So you see that you have a double angle. You have to ask yourself, does this fit into the multi-revolution, or should I change it? And since I have the other function cos squared, I'm going to change it to 2 sine x cos x. Nice thing about the half and the 2, they'll simplify. And so we have sine x cos x minus cos squared. And again, there's no way to change it all to one trig function, so we're going to have to factor instead. So I have a common factor of cos. That'll leave me with sine x minus cos x equal to 0. This part is going to be easy. Cos x equals 0. That happens when x is equal to 0. Pi and 2 pi. Oh my goodness, but our domain didn't include 2 pi. I love it when the textbook does that. I mean, it's kind of good because it teaches us that we should always read it again and check what it is. Look for that detail. Yeah, they're like, make sure, right? Make sure you're paying attention. Okay? This one's a little bit harder because sine x minus cos x equals 0. Can you see that you're really trying to find out this? When are sine x and cos x the same? If they're the same, then that will equal 0. So one way you could do this is just think about your unit circle. You said 45 degree or pi over 4 family, right? So x could equal pi over 4. Are there any other of your pi over 4 families where the x and the y coordinates are the same? 5 pi over 4, where they're both negative, right? So that's method 1 that you could solve this side. Or, can you see that if you divided here, I know dividing, I've already told you about being careful with dividing, but if you divided both sides of this equation by cos, you would get sine over cos equals 1. And sine over cos is the same as tan. Where is tan equal to 1? At pi over 4 and 5 pi over 4. So we could change that side to only tan. And the reason that dividing is okay on this side is because when you divided, something didn't cancel out. Right? When I divided both sides here by cos and I got tan, it's not like I canceled out my cos and made it go away. So that's where the dividing is dangerous, because you would lose a solution. But in this case, that doesn't happen, and we still get the same solutions. Now I have a ton of questions for practice for the weekend. So you have from your textbook 12, 13, 14, 15. And although the sub gave you these questions already, and you could do some of them, you couldn't do all of them. So on the back of your Identities page, maybe you wrote these ones down already, 8, 9, 11, 12, 14, 15, 21, 27, 29, 31. Okay? And you'll want to write those down because if you think, oh, I remember on the back there was a bunch of ones that were circled. Those aren't the ones that were assigned. I don't know why those ones were circled, but and that finishes chapter 7.